Welcome to the presentation of our paper titled An Evaluation of Methods to Port Legacy Code to SGX Enclave. My name is Kripa Shankar and I am a PhD student in the Department of Computer Science and Automation at the Indian Institute of Science, Bangalore. This is joint work with my collaborator Arun Joseph and supervisor Vinod Ganpati. We look at the problem of porting application to SGX enclaves. SGX enclaves are an example of hardware-based trusted execution environment. To motivate the setup of SGX enclaves and trusted execution environments, let us consider the following scenario. Suppose an organization has developed a deep learning model after extensive training and hyperparameter tuning. It wishes to offer its deep learning model as a cloud-based inference service. For this purpose, the organization hosts its machine learning model on a public cloud platform such as Google Cloud. On traditional public cloud platforms, the cloud provider has the privileges to peek into the container or the virtual machine of a client. It can steal or tamper the confidential machine learning model of its client. This poses a major barrier to the prospective clouds with sensitive data or code. This scenario makes public cloud computing platform unattractive to certain users and organizations that deal with private data such as financial institutions, healthcare, etc. To overcome this problem, Intel introduced Software Guard Extensions or SGX. SGX is a set of extensions to the Intel instruction set architecture that create enclaves. Enclaves are created as a linear region in the virtual address space of the process. The hardware ensures that any code and data that are placed inside this enclave are protected from even privileged malicious adversaries, including all system software such as the operating system, the cloud hypervisor, and the firmware. Roughly speaking, the hardware implements such protection by encrypting the contents of memory with a hardware protected key, introducing a new enclave execution mode and decrypting the contents of the memory only when the processor is in this mode. Therefore, SGX admits a very powerful threat model and protects applications code and data from even most privileged software on the system. Applications must simply place their private code and data inside this enclave and hardware takes care of the protection. However, SGX imposes certain restrictions. Not all applications can execute unmodified inside the enclave. In particular, certain instructions are no longer permitted when the processor is in the enclave execution mode. Our paper contains a full listing of the instructions forbidden in the enclave execution mode. However, the most noteworthy one is syscall instruction, which is used to make system call. As a result, any application that uses system call, which include almost all the applications, will not run out of the box within an SGX enclave. The only way to get the application executing within an enclave is to transfer the control to the process from within the enclave, thereby exiting enclave execution and have the process perform system call on behalf of enclave. The process obtains the return value from the operating system and then passes control back to the enclave. The return value are under the control of the malicious adversary and can be used as an attack vector too. Return value must be sanity checked before being consumed by the enclave. Given the problem of porting application to safely execute within the enclave, the community has come up with three models to allow application to be ported to enclaves. These are library OS model, the library wrapper model, and instruction wrapper model. These models have been evolved by the community over approximately the past 4 years. Each of these models differ in the amount of work they do inside the enclave before transmitting control to the supporting code running outside the enclave when the application wishes to perform a system call or execute a similar forbidden instruction from within the enclave. The porting experience with each of these methods is also rather different. In this paper, we will investigate the merits and cost of these models. We use concrete examples of each models in our evaluation. For library OS model, we use Graphene SGX developed by a team from the University of North Carolina, Chapel Hill. For the library OS model, we use Panoply, which was developed by a team from the National University of Singapore. For the instruction wrapper model, we wish to use Scone, a software package developed at the Imperial College London, but the code is not available, so we build a replica of Scone. We evaluate this model based on 4 research questions. What is the effort required to port an application, for example, code changes, setting changes, to obtain a working enclave? What is the effort required to re-engineer a working enclave, for example, by moving code into or out of enclave? How much trusted code does each method require, and what is the runtime performance cost of each of the 3 porting methods? In this presentation, we will primarily focus on research question 1, research question 2 and research question 3. We invite you to read our paper to learn about research question 4. Next, let us investigate in more details the 3 models that the community has proposed. We will start with the Library OS model. As the name suggests, the Library OS model uses Library OSs. Library OSs implement the bulk of the functionality of traditional operating system as user space libraries and relies on relatively small kernel to perform privileged operation. Graphene is one such library OS. The Linux kernel library or LKL is another popular library OS. In this model, the application is linked together with the library OS and any dependent libraries as a single entity. The whole entity executes within the enclave. The library OS run inside the enclave. Much of the system call handling code sits within the enclave. The library OS has a relatively narrow interface to the privileged kernel, typically consisting of few tens of interface definition. When a system call requires some privileged operation, for example, reading or writing a block of sector from a disk, the library OS exits the enclave via one of these interfaces and performs the operation outside the enclave. Some system call never crosses the enclave boundary. For example, dupe2, which duplicates file descriptor, can be implemented using a simple copy operation within the library OS itself. Let us now move to the library wrapper model as exemplified by Panoply. In the library wrapper model, only the core of the application and a small shim layer reside inside the enclave. Everything else, including all supporting libraries and the application needed for the execution, reside outside the enclave. The shim layer serves as the interface to the library which execute outside the enclave. The key idea behind the library wrapper model is that modern applications rarely invoke raw system call. Rather, they do via libraries such as GNU libc or muscle libc. Thus, in the library wrapper model, a shim consisting of wrappers that are written for library functions that the applications need to invoke. Consider an example of read function inside the enclave. In the trusted shim layer, which executes within the enclave, we see the wrapper of the read function call referred to on this slide as ocallRead. The ocallRead function leaves the enclave and executes the read function in the untrusted shim layer outside the enclave. When the read function returns in the untrusted shim layer, the results are copied back into the enclave. In this case, the buffer and the number of bytes read are copied back to the enclave. After this step, the control returns into the enclave and application resumes executing inside the enclave. Moving on to the third model, namely the instruction wrapper model. In this case, the application and its dependent libraries reside inside the enclave. In instruction wrapper model provides modified libraries in which low-level instructions such as syscall are wrapped suitably so that only their execution causes an enclave exit. This slide shows a snippet of syscall function from muscle libc which contain assembly code required to invoke a system call by invoking syscall instruction. Let us now look at the wrapper for the syscall function. The wrapper copies the argument of the underlying system call to a buffer outside the enclave. It then invokes ocall syscall, which leaves the enclave and actually invokes system call outside the enclave. The instruction wrapper model differs from the library wrapper model at the abstraction layer at which these wrappers are written. The instruction wrapper model has wrappers written at a much lower level of abstraction than the library wrapper model, that is, at the level of x86 instruction that perform the system call. Let us now move to the research question, which compare these three models from the perspective of an application developer. We start with the first research question. The first research question asks the following. From an application developer point of view, what is the effort required to port an application using each model? To answer this research question, we took a wide variety of real-world benchmark applications ranging from Python interpreter, Memcached key value store, Astro web server, and OpenSSL crypto utility, and attempted to port them to execute within the enclave using each of the three models. Let us start with the library OS model. We were able to port all the benchmark application using the library OS model. In this model, the application depend on the library OS for the operating system services. The library OS emulates several system calls inside the enclave itself. For those system calls that require support from the operating system, such as reading or writing a block from the sector on the hard disk, it exits the enclave and invokes system call from outside the enclave and then returns to enclave to resume execution. In fact, the Graphene SGX prototype of library OS model even provides binary compatibility. That is, it allows executable applications that have been suitably statically linked with the library OS to execute within the enclave. The source code of application is not required. Moving to the library wrapper model, as this slide shows, we were unable to port Python and Memcached with the Panoply prototype. There are three main reasons because of which it is challenging to port application to SGX with the library wrapper model. First, missing library wrappers. Second, deeply nested structure. Third, rapid evolution of APIs across library version. Let me tell you about this problem in the following slides. Almost all applications depend on libc. Libc itself contains around 2000 functions. However, our reference implementation of library wrapper, that is Panoply, has only around 250 wrappers. Without implementing more wrappers in Panoply, we cannot port applications such as Memcached and Python, and we have not attempted to write such more wrapper. In addition to libc, Memcached depends on libevent library. This library contains 9 function interfaces. The application developer has to add wrappers for the libevent library function used by the application. The second main problem with the library wrapper model is that of a deeply nested structures. Deeply nested structures are structures which contain pointer to the other structures. A simple example of such structures are linked list. It is challenging to write wrapper for functions whose argument contain deeply nested structure. The wrapper for such function must perform a deep copy of entire structure outside the enclave and perform a similar copy when the function returns. The third problem with the library wrapper model is the empirical evidence shows us that APIs of libraries evolve as library itself evolves. In this chart, we show the evolution of GNU libc API over 10 versions. On the left y-axis, we show the total number of API functions in each version of the library. As you can see, the width of API has increased from one version to another. On the right hand side, we show the number of functions added or removed from the API. Function wrapper must be added or modified in the shim layer when API is added or modified. In contrast to the evolution of libraries API, if we look at the system call API, it has evolved slower than GNU libc API. It is therefore easier to maintain instruction wrapper on or a library OS model API as compared to library wrappers. Here is a chart showing the total number of system call on left y-axis. The number of system call has increased from 333 to 345 over 9 versions. Only 2, 4 and 6 system calls were added in version 4.18, version 5.1 and version 5.2 respectively, and no system calls were removed. This shows that the system call interface evolved much more slowly than the library interface. When we considered porting application with the instruction wrapper model, we were able to port all the benchmark applications. This shows the benefit of wrapping at the instruction level as compared to the library call level. That concludes our discussion of the first research question, and now we will move to the second research question. In the second research question, we consider the following setting. Suppose that an application has already been ported for use within the enclave. The software maintenance team decide that it is not advisable to execute the whole application within the enclave. This could be for a variety of reasons such as performance, since applications execute slower within the enclave, or to deep load the enclave. The maintenance team decide that they want to re-engineer the application and execute only a small portion of application inside the enclave. For example, the part that handles sensitive data, but the rest of code should execute outside the enclave. They have also decided what exactly should run within the enclave and what should run outside the enclave. Given such re-engineering decision, how much effort would the software maintenance team have to invest to re-engineer the application? Let us consider a case study with the OpenSSL package. Suppose that an application developer has ported this entire application to the enclave, but the developer later decides that performance of OpenSSL has degraded due to the use of SJX. The developer then decides that it is only necessary for the security sensitive RSA key generation algorithm to execute within the enclave. What is the effort required to re-engineer the application given this new requirement? Application cannot be re-engineered with the library OS model as it was originally designed to run entire application within the enclave. Library wrapper and instruction wrapper model require wrapper for eCall to re-engineer the application. Let us look at this wrapper for OpenSSL case study in the next slide. For RSA key generation algorithm, only one function interface is required to the enclave. The application developer specifies the name of the function eCall genRSA main in the interface definition file. The interface defines the function that is used to enter an enclave and execute the corresponding function. Then application developer then update the corresponding file to call the wrapper function rep genRSA main. The wrapper function calls eCall genRSA main, which takes care of enclave ID as one of the parameters, enters the enclave and executes genRSA function inside the enclave. In this particular case study, only one interface was required and around 8 lines of code was added. Thus, application developer has to add these interfaces for the library wrapper and instruction wrapper model to re-engineer the application. This concludes our research question 2. We will now proceed to research question 3. Research question 3 asks the following question. How much trusted code does each method require? In this, we only consider the code of porting framework. We exclude the source code of application itself as it changes from one application to another. This table shows the source line of code of different components of each model. The library OS model has largest amount of trusted code as entire library OS reside inside the enclave. Library wrapper model has least amount of trusted code, which consists of function wrappers. Instruction wrapper model comes in between library OS and library wrapper. In instruction wrapper model, trusted code consists of modified libc and sim library. This concludes our research question 3. For research question 4, we invite you to read our paper. To summarize our finding, we conclude that there is no one porting model that works best for all the 4 research questions that we consider. The specific model to be chosen depends upon the goal and the resources available with the software engineering team. If the goal is to rapidly prototype an enclave version so as to obtain a quick fix for the security, then library OS and instruction wrapper models provide the convenient method to get application up and running inside the enclave. For application re-engineering, the library OS model and instruction wrapper model present identical porting experience. The library OS model is not tailored for application re-engineering. As far as supporting infrastructure itself is concerned, the library OS and instruction wrapper model present the best option because the system call interface evolves slowly. If the source code is not available, then the library OS is the only option currently available. We thank all of you very much for your time. To read all these results in more detail, we invite you to read our paper. Please follow the QR code shown in this slide for links to our paper and associated artifact. We have archived all the code and the data used for this paper. So we invite other research group to replicate and extend our research.